Definition. In Faraday's experiment with two coils on a conducting iron ring, he discovered that a changing magnetic field in one coil induces an electromotive force or voltage in the second coil. This phenomenon is called mutual inductance. Mutual inductance occurs when a changing magnetic field in one circuit induces voltage in a nearby circuit. When voltage is applied to the coil on the left, a magnetic field is induced in the iron ring. As the field is expanding, a voltage is generated in the second coil on the right. This secondary voltage causes a current flow in the second coil. This secondary current flow is in the opposite direction of the current flow of the first coil. When the induced magnetic field in the ring becomes steady, current ceases to flow in the second coil. When the current in the first coil is switched off, the induced magnetic field in the ring begins to collapse. As the field is collapsing, it again generates voltage in the second coil. The resulting current flow in the second coil is in the opposite direction to the previously induced current. When the magnetic field in the ring is fully collapsed, the induced voltage and current flow in the second coil also ceases. Consider an experimental setup when two conducting coils or solenoids S1 and S2 are placed coaxially. The dimensions of the two solenoids are shown in the table. When a current I2 is set up through S2, it in turn sets up a magnetic flux through S1. Let us denote it by Phi1. The corresponding flux linkage with solenoid S1 is N1 Phi1 is equal to M12 into I2. M12 is the mutual inductance of S1 with respect to S2. M12 is also called the coefficient of mutual induction. Magnetic field in S2 due to I2 is mu naught N2 into I2. Flux linkage with coil S1 will be N1 Phi1 is equal to N1 into I into pi R1 square into mu naught N2 I2. Comparing the equations, N1 Phi1 equals M12 into I2 and N1 Phi1 equals mu naught N1 into pi R1 square L into I2, we can say that M12 is equal to mu naught N1 into pi R1 square L. Note that we have considered L to be much greater than R2. By taking L very large compared to R2, we have assumed that the magnetic field is uniform throughout the length of the solenoid, neglecting the weakening of the magnetic field at the edges. This weakening of field is also termed as edge effect. Now consider the case when current I1 is passed through the solenoid S1. The flux linkage with the coil S2 will be N2 into Phi2 is equal to M21 into I1. M21 is the mutual inductance of S2 with respect to S1. Flux in S1 due to I1 can be assumed to be confined solely inside S1 since the solenoids are very long. Thus, the flux linkage with S2 will be N1 Phi1 equals N2 into L into pi R1 square into mu naught N2 I2. N2 is the total number of turns in S2. Comparing the equation, N1 Phi1 equals M12 into I2 and N1 Phi1 equals mu naught N1 into pi R1 square L into I2, we can say that M12 I2 is equal to mu naught N1 N2 pi R1 square L into I2. M21 equals M12, that is equal to M, where M is equal to mu naught N1 N2 pi R1 square L. The above experiment is carried out in air. If this is carried out in a medium with relative permeability mu R, then the mutual inductance will become mu R into mu naught N1 N2 pi R1 square L. Now you can understand that the new term mu R is added to the original value of M. The box containing medium with relative permeability mu R. If current varies with time, then d phi dt is di dt. Current I2 is passed through S2. N phi 1 is equal to M into I2. dN phi 1 by dt is equal to dm I2 by dt. We know that induced EMF in S1 is given by epsilon 1 is equal to d by dt of Ni phi 1. Epsilon 1 is equal to minus d by dt of Mi2. Therefore, epsilon 1 is equal to minus m into di2 by dt. It shows that the varying current in one coil can induce EMF in a neighboring coil. The magnitude of induced EMF depends upon the rate of change of current and mutual inductance of two coils. Concept: two concentric circular coils, one of smaller radius R1 and the other of larger radius R2, such that R2 is much larger compared to R1, are placed coaxially with centers coinciding. Obtain the mutual inductance of the arrangement. Solution: let a current I2 flow through the outer circular coil. Then B2 is equal to mu naught I2 by 2 R2. Phi 1 is equal to pi R1 square B2, that is equal to mu naught pi R1 square by 2 R2 into I2, that is equal to M12 into I2. Therefore, M12 is equal to mu naught pi R1 square divided by 2 R2.